Welcome back, guys. Hopefully you watched the Khan Academy videos last week, so you got a pretty good introduction into double integrals and calculating the volume. If you remember from 14.1, we started taking double integrals and setting them up, and we found the area. And the area was found by writing the double integral with no function right here. So now with volume, you find the integral, the double integral, sometimes triple integral, and you put the function here. And you'll be given some limits for r to set up your integrals. So let's take a look at a couple examples, and then you'll have some to practice for homework, and I'll post some of the even solutions on the portal. So this one we've got, evaluate the integral 1 minus 1/2 x squared minus 1/2 y squared, where r is bound by 0 to 1 and y is bound from 0 to 1 also. So I always draw a picture. So x is bound from 0 to 1 and y is bound from 0 to 1. So it makes a rectangle. So it doesn't really matter which one comes first at this point, because I can either I can either go this way with my volume and go up towards z, or I could go this way with my volume and go up towards z. So remember, your z-axis is like out, right? So this yellow triangle would be coming towards us, following this function right here. So maybe it's like a paraboloid or something, and so this little rectangle would be getting smaller as it went out towards the tip of the paraboloid. So you just have to decide, do I want my green rectangle to come up from the surface, or do I want my yellow rectangle to come up from the surface? So I'm going to do dx first and then dy. So I want my x limit and then my y limit. So I'm going to take the integral, both of these are 0 to 1, of 1 minus 1/2 x squared minus 1/2 y squared. I'm going to do dx first, then dy. So let's do just the dx part first. So this becomes x minus 1/2 x cubed over 3 minus 1/2 y squared x from 0 to 1, plugging in 1 and 0 for x. So I'm just going to simplify that a little bit. X minus x cubed over 6 minus 1/2 y squared x from 0 to 1. And when I plug in 1, I get 1 minus 1/6 minus 1/2 y squared, and then minus 0 minus 0 minus 0, so that's just 0, luckily. So 1 minus 1/6 is 5/6 minus 1/2 y squared. Now I'm going to take that integral with respect to y. Now take the integral of this, so you have 5/6 y minus 1/2 y to the third over 3, evaluated from 0 to 1. I'm going to simplify this a little bit. So I have 5/6 y minus y to the third over 6 from 0 to 1. So I'm going to plug in 1. 5/6 times 1 is 5/6 minus 1/6. And then plug in 0, all that just becomes 0. So 5/6 minus 1/6 is 4/6, which simplifies to 2/3. Now, if you went and found the integral where you did y first and then x, you'll end up with the same answer. So in this case, it didn't matter which one you used first. They were of equal simplicity, but sometimes you might want to set up both and just kind of preview what you think the integral is going to turn out to be, and see which one's going to be easier algebra-wise. Let's look at one more example. So write both orders of integration and choose the simpler integral to evaluate. the volume of the solid region bound by the surface e to the negative x squared in the planes z equals 0, y equals 0, y equals x, and x equals 1. So the z equals 0 part doesn't necessarily matter. We're just finding the volume of this e to the negative x squared. So ignore the z equals 0 part. That's kind of irrelevant at this point. So let's draw a picture first. That's what I always do. So we know we have the line x equals 1 and y equals 0, and the line y equals x. And so this is the region they're worried about. Let me highlight that instead. So here's the region we're trying to find, and that's going to be coming, we're going to find the volume of that. And so you could either do this rectangle coming out towards us, or you could do this rectangle coming out towards us. And so I'm going to set both up and see what happens. Let's look at the boundary where the red rectangle. Okay, so the red rectangle, you've got x goes from 0 to 1, and y goes from 0 up to that green line, which is y equals x, so up to 0 to x. So that'll be an e to the negative x squared dy dx. So the red rectangle was a vertical rectangle, so that's with respect to y. Now let's look at the blue rectangle. This one, you've got a horizontal, so your x is actually going from y up to 1, and your y goes from 0 to 1. And so that's going to be e to the negative x squared dx dy. And so just looking at this, I already know that the red integral is going to be easier, because the blue integral is going to require a whole lot more work, whereas the red integral, because I'm taking the integral with respect to y first, I end up with that extra x in there, and then you'll be able to use substitution. So now let's evaluate this integral. I'm going to erase the blue one because that one's more complicated, and just do the red integral. So let's do the inside part first with respect to y. So that means e to the negative x squared is a constant in this integral. So I end up with y e to the negative x squared from 0 to x. And so that ends up being x e to the negative x squared minus 0. And now I'm going to take the integral of that from 0 to 1. So I'm going to use u substitution. U equals negative x squared. And that means u of 1 is negative 1, and u of 0 is 0. Du dx is negative 2x, and I'm going to isolate dx. Okay. Notice how my integrand is going to be upside down, so I'm going to have to flip that too when we get there. So now I'm going to do it on the left here. I've got the integral from 0 to negative 1, x e to the u du over negative 2, x. Left out the x there. Well, the x's cancel, and the negative will cancel when I flip the integral, because technically I'm going to have to change this. And so the negatives will cancel. So now I have the integral from negative 1 to 0, e to the u with a 1/2 out front, du. And so that's 1/2 e to the 0 minus 1/2 e to the negative 1, which is 1/2 minus 1 over 2e. And I'm just going to leave it like that. And that is your final answer. So I want you to try some of the book problems. Some of them are going to be more complicated than others, so I just want you to, you don't have to sketch anything, and unless you don't have to sketch the actual functions, but I want you to sketch the regions that are bounded. So you're going to try some of the 11 through 17 problems. I'll just give you a warning that like 14 requires integration by parts. You might not want to do one like let's see, the rest of them don't look too bad. Number 13, you'll have to break up into 3 separate integrals. So I want you to give these a try for homework, and I'm going to post some of the answers on the portal as well. So good luck. Don't forget to reach out if you have any questions.